This presentation looks at some trends and insights gained from monitoring wastewater within the sewer network. This study was performed within Peel region. This is an upper-tier municipality encompassing 3 cities, Brampton, Caledon, and Mississauga, for a total population of 1.5 million people. Our famous neighbor immediately to the east is the city of Toronto. The presentation has 3 parts: introduction to sewers and sewer monitoring, a review of trends and insights, and it concludes with the next steps. There are cool sewers that you see in the cartoons and Walt Disney movies. Then there are really large sewers like the one in the middle of the screen. But the truth is that most sewers are small and unglorified. If there's one thing that you take away from the presentation is that for the sake of sewage heat recovery, only large sewers count, not the rest. And large means anything bigger than 650 millimeters in diameter. Sewer networks are very much like a tree, where your home is just a leaf connected to a small branch. Small branches come together and make bigger branches that lead to the trunk. Sewers are just like the branches. They change in size, and the bigger ones are referred to as the trunk. Sewers are also like one-way streets. Flow only goes downhill, or at least that's the intention. All sewers end at a treatment plant which treats the sewage and discharge the outcome, referred to as effluent, into the lake. What you see on the right side is one branch stretched from the treatment plant all the way to the thin end to where the buildings are located, where the leaves are. This slide shows 2 opportunities related to sewage and wastewater networks. The one on the top is the Falls Creek District Energy Network in Vancouver. In this case, energy is harvested from raw sewage. An energy recovery facility is built to draw raw sewage from the sewer, screen the solids out so it can be pushed through the heat exchanger, and after the heat is exchanged out of the flow is sent back to the sewer. The harvested heat then is used in the district energy system to service the community. The case at the bottom is the Lakeview Village project within our jurisdiction, Peel region. This project is going to harvest heat from effluent, treated wastewater. In this case, there is no need for an additional energy recovery facility as the treatment plant takes care of all of that work. The effluent goes into the energy center and comes back to the plant for discharge to the lake. This study and presentation looks at the temperature of the sewage within the sewer network. So this is more applicable to identifying opportunities like the one at the top, the Falls Creek in BC. We are monitoring depth, velocity, flow rate, as well as temperature of sewage within our network at over 400 locations. This involves descending into the sewer and install equipment, and then maintain it on a regular basis. This is quite a shit show, quite literally. Things break all the time and go wrong all the time. That's why this initiative, the monitoring, costs more than $4 million every year. However, the data collected enables us to operate the network very efficiently. We use it for all different purposes. All I'm going to explain on the temperature side of analyzing the data has been done 100 times over for other parameters. This is our first attempt at looking at the temperature side. This study isn't the expensive part, it's the monitoring portion that is very hard and costly. 50 monitoring locations were selected for this study. Care was given to pick locations from different land uses, different pipe sizes, and different vintage ages. This allows us to slice the data by, for example, land type, and then see if there's a correlation between residential neighborhoods and the size of the pipe, or so on. It is evident that this type of work requires professionals who are both very smart and dedicated. Kristen, Ashley, and Dave have done the work I only dream of the project and they make it a reality. They deserve all the credit here. The presentation has three parts: introduction to sewers and sewer monitoring, a review of trends and insights, and it concludes with the next steps. The general approach to the study is intuitive. What may need a bit of explaining is the difference between dry and wet weather. As the name suggests, wet weather refers to data collected when there are precipitation like rain and snow. Wet weather activities make a difference in flow regime inside sewer, including its temperature. Given that no two storms are identical, storms shall be qualified, which makes the topic even more complex than it is. I'm going to spare you all such details and directly get to the point. Though we have a long report that explains all the assumptions and underlying conditions, and it's very important to keep those in mind for those who want to dig in deeper, because statistics without a statement of the assumptions is a dangerous thing. Two completely contradictory conclusion can be drawn from the same data set, and that is not our intention. First trend is seasonal variability. A consistent 2 months lag is evident between change in temperature, shown with the blue line, and the flow temperature. The three charts shown monitoring data are from residential, ICI, and mixed land use types from top to bottom. Small pipes tend to carry warmer sewage, but their high and low over a given day is really far apart. ICI has a tighter variation, but the overall flow is a bit colder, and the mixed areas, which often are on larger trunks servicing a big area, are the most stable. The temperature seems to be stabilizing around 20 degrees and does not vary from between the times of the day, and the size of the sewer do not make as much of a difference. There seems to be a weak negative correlation between amount of dry weather flow and its temperature. Less flow means higher temperature. We're going to look at a few trends for wet weather flow. The rainfall event is shown with the blue at the top of the chart. The black line shows the typical temperature and the blue shows the observed temperature during the wet weather event. And the bottom left, you see the subtraction of the two from each other. This much is going to be repeated in all the trends that we are going to look into in the future slides. What we are going to focus on are a set of variables explained individually in each slide. The first one is magnitude of drop in temperature. During storm events shown, during the storm events, and it's highlighted in green on the slide. It is evident that the temperature drops by no more than 2 degrees in this example. Please note that the trends are based on analysis of multiple storm events and multiple monitoring stations. What is shown here is just one example for the sake of explaining the concept of variable and concept. A clear trend is observed here. As the catchment grows, the impact of rain on temperature is reduced. In other words, at the treatment plant, we see no change in temperature for most rain events happening upstream in the system. Duration of the falling limb is defined as the time between start of falling limb, usually close to the start of the rainfall event, and the start of the recovery limb. There's a clear trend observed here. For smaller catchments, the variance drops quickly and deeper. For larger catchments, it drops slower and not as far. Duration of recovery limb is between the start of recovery and end of recovery, or start of the next event, should that happen. There is a tangible trend here. It takes longer to recover if temperature has dropped significantly. Also, more rain means longer recovery period. The variance in question here is the length of time that drop in temperature remains more than half a degree Celsius. The same is also done for 1 degree. And the results are tabulated here along with everything else that we discussed and much more information. What I want to draw your attention to is at the bottom of the table regarding duration of temperature drop beyond 1 degree Celsius. You see that there is no trend observed here. And I want to emphasize that this is just as significant as some of the other more strong correlations. It means that we cannot blindly extrapolate from some observations to deduce information on the other ones. It also suggests that there may be other control measures that we have not considered and we should consider in our future studies. One takeaway that I can leave you with is that size matters when it comes to this topic. Size means more stability on various fronts. The presentation has 3 parts: introduction to sewers and sewer monitoring, a review of trends and insights, and it concludes with the next steps. We have simplified all of this in one figure that shows the amount of energy that could be harvested at any given point in the system. Though you know by now that this is a lot more involved and there's much more to be studied before making a decision. The bottom line is that opportunities like Lakeview Village are more reliable than the other ones relying on sewage. We're going to build upon this experience and keep digging in the data for other insights and learnings. We're also building a dynamic model of sewage temperature, not just a static model that is common, a dynamic one to better understand the network. And we are going to do all of this for the water network as well, so stay tuned. The presentation has 3 parts: introduction to sewers and sewer monitoring, a review of trends and insights, and it concludes with the next steps. Thank you very much.